The one question that came from you midway through the course was about the concept of heatlines. This came up twice, and I promised that I'll talk about it. And I decided to do a serious job of answering that sort of suggestion, because the story of heatlines is important for every single person who contemplates a career in free thinking and, research, science, university or research laboratory, where physically and by definition you are alone. That is, if you're a free thinker, you're alone. You're not a sheep. You don't need a shepherd. And that is, that was my position. So, heatlines. It starts with the classical concept of streamlines. Streamlines, this is from the 1800s. They're beyond classical. In the 1800s, that was the period when the calculus spread with some difficulty, but it did spread. And the idea, is very simple. Here's the mass conservation equation with, in the simplest setting, which is two-dimensional flow, steady state, almost constant property, du dx plus dv dy equals 0. And the unknowns are the temperature field, velocity components, and the mathematical simplification, which I'm repeating now, was to introduce a function, to invoke the existence of a function such that u is partial of psi dy and v minus d psi dx, such that when substituted into the mass conservation equation, this trick guarantees that the mass conservation equation is satisfied for all combinations of u and v. In other words, you simplify your arsenal of, that's called a weaponry of mathematical analysis by reducing, basically we have three equations, mass, momentum, and energy, reducing the 3 to 2, you see. And I presented this, obviously by parroting the classical presentation. However, and here now I become autobiographical, the problem with calculus, in fact, I commented on algebra, where it came from, kind of a symbolic language of, of geometry. Algebra came from drawings. And when encountering this kind of thing, and this is happening often in your education today, math on top of math, and now with software, we don't even question what's inside the box that gives you answers. I remember at the start of my career that when presented with math, I asked, where is the drawing? Yeah, where is the drawing? Oh, education is full of patterns of streamlines. Yes, you've seen them. But where do those come from? What exactly is the connection between the math and the things that you're seeing? And so this is how I begin today's lecture. Well, the drawing becomes apparent. I don't know whether you've been taught this way, but here's the way that I was thinking. leading to Heatlines, which I published in 1983. If I substitute, so first of all, if I take the differential of deep psi, and clearly it's deep psi, the x dx plus deep psi dy dy. Obviously on the right, I will put here minus b. And over here, u dy. And of course, deep psi is here. And now, if I make the additional assumption that this stream function has a constant value, meaning psi constant, it means that on the left-hand side, I get 0, you see? And this dy divided by this dx is equal to v over u. In other words, there is something else. To give a constant value to psi, remember, psi function of x and y is now constant, is another way of saying that there's a curve y of x in the two-dimensional plane. A curve called psi equals constant. And, we're on that curve with this kind of a And the ratio of v divided by u, here is the v, at this point called xy divided by u, that happens to be the slope of the trajectory called psi that passes through this point. So here, that is the drawing that's behind this kind of mathematics. The definition of velocity components in terms of as derivatives of psi is a let's call latter day rewriting that came from this mental viewing, which was a drawing. Here is the way in which to describe the flow field with a family of curves. One value for this particular psi, or for that matter, here's another curve called f of psi 2, this is psi 1, for another value of psi. So you have a, from the, let's call abstract, juggling the ball on stage, you've seen these comedians. From that, you have something that's palpable, and you see it, in fact, every evening when you watch weather news. You see patterns of the wind pattern on the in the country or on the globe. Get it? And of course, if the flow field is time dependent, these they look like bundles of hair, flailing in the wind. All right, so that's the background. But the message from the background is that behind the mathematics, there's a drawing, a mental viewing before the drawing. And since it's an old idea, people forget the drawing. If if you get interested in this true origin of mathematical analysis, without which there is no fluid mechanics, then study the history of science. The book of Newton on the continent it's called Principia. In England it's called Principia. I don't know. Even though I lived back then, I don't remember how they were speaking. The point is that book has none of this mathematics. It's expressed in drawings. Yep. All right. Another one of my heroes happens to be English as well. Maxwell, in thermodynamics, known for his equations and all sorts of other things, expressed himself this way with drawings. Yeah. Pretty cool, huh? All right. So now here comes this novice in 1983, moi. And I said, well, heat is being convected, right? What is the pattern of heat flowing through a flow field? Everybody knows the so-called heat flux lines in conduction. But conduction is through a medium that's not moving. Clearly, it's just like the wind. If you imagine here the wind moving these things, clearly if there's flow, then this flow will wash away the heat flux lines of heat conduction. And can you guess how long it took to do the convection equivalent of this? I don't remember how long, but it was definitely very, very short. Here's that part of the story. In fact, the story is not discussed specifically, but if you read those of you who have the textbook and the preface to the 4th edition, I talk about the fact that at the time I was beginning my career at the University of Colorado, and I was still playing basketball very seriously, and I ruptured my Achilles tendon. So therefore I became wheelchair bound. So that was a very productive period in my teaching. And I had a Japanese PhD student who would meet me at the curb and wheel me to the classroom. Shigeo Kimura, he will appear very soon on the blackboard. And I did a lot of work because I was, confined in this very small space with my thoughts. And this is one of the things that I came up with. Let's look at the energy equation for the same two-dimensional flow field, time independent, with nearly constant properties. The energy equation is more complicated, of course. Here's the energy equation, goes like that. By the way, you can do this for time average turbulent flow, same thing, because the equations have the same shape, but that's for later. Here is the equation that we've been solving. Convective terms here. And then alpha is the thermal diffusivity. And then d2t dx2 plus d2t dy2. This alpha is the ratio of thermal conductivity divided by the heat capacity of the fluid. Remember now, this product is called heat capacity. C sub P by itself is specific heat. If you read the research articles, you'll discover that people mix those two concepts as if they're a single concept. Sometimes they call it caloric value, which is even worse. But be very careful. So yeah, here we go. Let's go through this sort of discovery. Remember, every course you take, if the professor is liberated in his mind, is really a bag of tricks or secrets that you learn only in this course. And there are several secrets called adding zero is okay. It is adding zero to something is okay. You can always add zero. You can also subtract zero. The other class of tricks is you can always multiply by 1, and you can also divide by 1. It's okay. In this case, the zero we add is T times the left-hand side of the mass conservation equation. And then on the left-hand side, you arrive at partial with respect to x of the product ut, and then plus product vt. And then the right-hand side is the same as before. This was the right-hand side. Actually, all of this is the right-hand side. You get the idea. And then it is from this level down that we combine the one term from here with one term from there, and so on, and rewrite the energy equation as d with respect to x of rho Cp, this rho Cp times ut, you see, ut, then minus from the right-hand side, k partial of t with respect to x, and then plus d with respect to y of rho Cp v t minus k and then partial of t with respect to y. And this stage, we imagine a function h of x and y. This is called the heat function. That is defined in such a way that the energy equation is satisfied identically for all values of this capital H. And we do that by calling this particular group dH with respect to y, and this other one minus dH with respect to x. You see here we're stepping into the footprints of those from the 1800s. So what I wrote is this: the partial of h with respect to y equals rho Cp u, and by the way, and then instead of T, because temperature, you see this in steam tables or in the thermometer, those numbers that they signify degrees or whatever name, Fahrenheit, Rankine, Kelvin, and whatever, Celsius, those numbers are relative to a reference temperature, the freezing point of water or some, alcohol back in the earlier days of thermometry. So T minus the reference, this number called temperature, is with respect to a reference temperature. And then minus K dt dx, and then similarly minus dH dx equals rho Cp, and then T minus T reference minus K dt dy. Now, if you go through the steps that I erased, you and if you, by the way, if you call this entire group the heat flux, remember heat flux, but this time is by convection in the x direction, to use the nomenclature from heat conduction, okay? See, heat flux in the x direction, this would be conduction. Now it is affected by convection. And all of this is the heat flux by convection in the y direction. I'm talking about this entire expression. And you have this psi, of course, the total differential is partial of psi with respect to x dx plus partial with respect to y dy. You replace the first factor with with minus this heat flux, and then you replace the other one with Q double prime convection in the x direction. And then finally, if you assign a constant value to this psi, constant, you made the same discovery that as the one that I erased here, that you make the discovery that the slope dy dx, the slope of the line, no, psi, h, what am I doing? Of course, what I'm doing is I'm parroting the pioneers. The constant h line has the slope heat flux in the y direction divided by heat flux in the x direction. In other words, the drawing speaks better. If this is the direction of heat transfer vertically, and this one horizontally, then the true direction of the h constant line is the one that I drew on a graph of y versus x. We can do all this as a consequence, or let's say because we're enabled to do it, because at this stage we possess the information on the flow field. So if the flow field, which means U and V, are known, that if also means, could be stated, if you know the stream function, then through this transformation, you also know the heat function distribution. So then you know h of x and y. So this is a heat line defined this way. And the pattern that you get, one heat line for every value assigned to capital H, is the pattern of how heat is convected by that flow field. Get it? The idea is as simple as the stream function idea, except that it has not been, how should I say, this connection has not been made before. I'll get to that aspect of academic research behavior in just a second. Now, why is this sort of development interesting, or useful even today? On the same weather news, you keep seeing the temperature distribution all over the country. You may see they show you the isobars, meaning the pressure distribution. If you know the pressure field over the United States, you get an idea of the direction of the wind, you see. Now, why is there a non-uniform pressure distribution on the surface of Earth? Did you ever think about that? Let's see whether you know elementary fluid mechanics, which begins with hydrostatics.
Isn't it just like surface roughness from...
No. What?
Is it because of the heat exchange with the surface? Like variable heat exchange with the surface?
What?
Is the wind caused by variable heat exchange?
No. I gave you a hint. Hydrostatics. The pressure on Earth, this is from Torricelli, the guy who invented the barometer, and then demonstrated it. By the way, there was another guy who demonstrated it. His name was Pascal. You've heard of Pascal? He was so rich he didn't have to work, so he had the time. He was the first mountain climber. Yeah, this guy, Pascal, Blaise Pascal, invented mountaineering, or the tourism for that matter. And he took Torricelli's apparatus from ground level to the top of the mountain and demonstrated that indeed the pressure in the atmosphere decreases as you climb. So here you are at the bottom here with higher pressure here today and maybe lower pressure other days. Irregular, like the weather, you see. And it is because the upper, meaning the thickness of the atmosphere and the density, because due to temperature, okay, you mentioned temperature, those things vary over time. It's like imagining the upper surface of the atmosphere being wavy. Wavy as the winds are blowing, or if you cannot imagine that, you imagine an atmosphere that's here cold, meaning air is colder, therefore denser, compared with over here. Yeah. And so these variations that you measure at the ground level have to do with the entire shell of moving air on top of this other shell that I call an eggshell, much, much thinner, relatively speaking, than a real eggshell. Okay. So yes, weather pattern graphics, those of you who know software developers could use or should use this technique to show not winds, but to show winds that will heat you or winds that will cool you. Back in 1993, Shigeo Kimura was spending more time with me than usual because he took care of me. So meaning I was not alone. My wife had just given birth, so she was busy with other duties. But Kimura was very good at what today is called computational fluid dynamics. Back then, graduate students had to build their own computer program to simulate whatever. For example, to put these 3 equations on computer and ask the computer to make some plots. So the kind of an exercise problem in natural convection, that's in chapter 5 in the book, was heat convection in an enclosure. An enclosure heated from the left, high temperature, low temperature, insulated top. And yes, you can solve the steady flow field inside such a box. And meaning you have a boundary layer on the left, another one on the right. And this circulation, which is like the peels of an onion, would go like this. So this was the field of, or the pattern of streamlines. Okay? Also classical, meaning known before Heatlines, was from heat conduction, the temperature field. The temperature field was this way. Anyway, this, you'll get the idea. Boundary layer here, meaning warmer, in other words, stratified. Stratified vertically. But you see, and of course, this is the temperature field. So streamlines and isotherms. This is the classical representation, I mean, the graphic representation of convection throughout this field. Well, heat lines. To plot them, you have to recognize that there is a tacit assumption of a reference temperature. And in making this next pattern, the Kimura and I numerically chose this one to be the reference temperature, meaning that there was a temperature called delta T on the left and 0 on the right. All right, and the heat lines that popped up for the first time in history were these. You see, and there's a circulation here that's kind of meaningless. So now you see how heat is traversing the box from left to right. First across this upward boundary layer, and later across the descending boundary layer. Key observation is that the heat lines at the wall are perpendicular to the wall because right at the wall the heat transfers by pure conduction because the fluid sticks to the wall and the wall is impermeable. Get it? So that was the first publication, and I moved to Duke in '84. And I got other ideas, so I didn't forget about this, but I got other ideas. But then I had another student who was very good at CFD, Alexander Morega, and he, in exactly 10 years later, did and published the same sort of 1, 2, 3 for the topic of chapter 2, which is the thermal boundary layer. The thermal boundary layer, if you are to make equivalent drawings, they would look like this. This is y versus x. The streamlines, well, the streamlines that arrive from the left are parallel, and because of viscosity near the wall, they are deflected slightly upward. These are the streamlines. The temperature variation, if the wall is, well, in this case, let's say that the delta T is here, and you see you already have a reference temperature here, which is T equals 0 in the free stream, then the isotherms would look like this, because heating proceeds upward. Get it? All right. And if the wall is hot, in other words, cold free stream, the heat lines look like this, but not exactly. If this is the velocity boundary layer, then the heat lines look like this, with the observation, one more time, that they are perpendicular to the wall, because at the wall the heat transfer is by pure conduction. So that's a hot wall relative to a cold wind blowing by. So you see, heat lines, unlike in the classical representation, distinguish between heating the surface and cooling the surface. So if the in this case, the wind that blows is cooling the surface because the surface is hot. If the surface is cold wall, and the incoming fluid is hot, then the heat lines look like this. They sink into the wall, and they come from farther and farther because the boundary layer becomes thicker and thicker to the right. All right? So these are heat lines when the wall is being cooled, heat lines when the wall is being heated.